Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to kind of pick up where we left off last time with our fundamental equations of thermodynamics and apply a little bit too much multivariate calculus. So today, before we can do this, we need to go over a cool feature of calculus known as the idea of an exact differential. So one of the big things that we can make use of is almost all of our thermodynamic functions that we care about are state functions. And these functions have what's called an exact differential. So again, if I have a state function, if I go ahead and integrate the derivative, that means that it will just be equal to the difference of the final and the initial state. I don't have to worry about the path or anything finicky. Now, if I have something that's a state function, it satisfies what is called the Euler condition. And that means that if I do a multivariable mixed derivative, so for example, if I look at the arbitrary function f, it doesn't matter whether I do the derivative with respect to y first or the derivative with respect to x, as long as I do one then the other. This is, you can kind of think of the commutative property, but for derivatives. So if I have a state function, this satisfies the Euler condition, and it doesn't matter which order I have the derivatives. Both will be equal to each other. And this is a very nice feature, especially considering that, hey, we're dealing with a lot of multivariate state functions. So let's take a look at our internal energy. So we know that internal energy varies as a function of volume and entropy. Well, what this means is I can go ahead and do the derivative with respect to entropy under constant volume, and then do the derivative with respect to volume. Or if it's easier, I can do the derivative with respect to volume, keeping entropy constant, and then do the derivative with respect to entropy. Now, either one should be equivalent, so it doesn't matter which derivative I take first. And this is a very nice and powerful feature because, as we've seen before, there are some times where it's going to be easier to do one derivative than the other. But there's another fun thing we can do with this. And this is that we actually were able to, through our fundamental equations, figure out what each of these first derivatives are. So let's take a look at our fundamental equation. Well, we know the derivative of internal energy with respect to volume under isentropic conditions is just pressure. So if I take this idea of the Euler condition, I can then go ahead and insert what I know for the derivative of the internal energy with respect to volume and the internal energy with respect to entropy. Because it turns out that this first one is just negative pressure, and the second one is just temperature. So I can literally insert these expressions in there. And then again, because I'm left with a single variable inside the derivative, I know that the derivative of pressure with respect to entropy is just the same as just the negative of the derivative of temperature with respect to volume. Now, it is worth noting there's a little extra feature here, uh, which is the idea that we're going to have to assume I'm keeping the other variable constant. So if entropy is changing here, I'm assuming I'm keeping volume constant. If volume is changing here, I have to assume I'm keeping the other variable constant, which is entropy. Now, one of the reasons why these relationships are going to be very powerful is because oftentimes we don't know about the variance in entropy, but we will know about the variance with respect to temperature and volume because I can measure these. So as a result, these expressions are really powerful. And they have a special name. They're called the Maxwell relation. So this is one of our Maxwell relationships, and it's going to tell us how we can look at pressure, volume, temperature, and entropy. But here's the thing. There's four fundamental equations, which means we have four different Maxwell relationships. Each one will go ahead and give us the variance with respect to the variables of question. So internal energy tells us how things change with respect to volume and entropy. Helmholtz will tell us about volume and temperature, enthalpy, pressure and entropy. and Gibbs pressure and temperature. So each of these has their own particular benefit. And you can derive each of them by literally saying, let's take an example of enthalpy. We're looking at how volume changes as a respect to entropy and temperature as pressure. So temperature, pressure, volume, entropy, and we have to keep the other one constant. So again, I just derived the Maxwell relationship for enthalpy, and we can do the same thing with Helmholtz. Notice that in the Helmholtz and uh, the case of Helmholtz and enthalpy, these will be positively correlated, no negative signs, because in Helmholtz we have two negatives and in enthalpy we have none. Gibbs and internal energy, though, will have a negative relationship in between our variables of interest. Now, these are going to be very useful because, again, you can imagine something. Let's take the Helmholtz as a great example. I want to know how entropy changes as a function of volume, but it's very hard to measure entropy. What's very easy to do is measure the change of pressure and temperature. And so, hey, we actually know good ways to determine this. And so this becomes very powerful. And there's lots of very nuanced ways we can explore how we use the Maxwell relationship. So let's go ahead and use our Maxwell relationships to derive an expression for one of our old friends, the uh, the internal pressure. So what we can do is let's go ahead and start with our fundamental equation for internal energy. Now I want to go ahead and figure out how my internal energy changes as respect to volume. So I'm going to divide all sides by dV, which will go ahead and remove the dV term on this far side, but it does so by introducing it over here. So I'm now dividing the internal energy with respect to volume and entropy with respect to volume. I'm going to do so by holding temperature constant on both cases. I'm going to keep that as my fixed variable. And now we've got a decent relationship for how internal energy changes as a respect to volume under isothermal conditions. All right, this should be fairly useful. Now, to do so, we have a series of variables. Now, these two are relatively easy because this comes from our fundamental equation. So the first one is just going to be temperature, and the second one is negative pressure. These come straight from our from our fundamental equation. This change in entropy with respect to volume is a little tricky. But as I said, if you're trying to figure out how entropy changes, Maxwell relationships are a good place. And we're looking for how it changes with respect to volume and temperature. Well, now we can go to vat ugh shit. And we know that Helmholtz is in between volume and temperature. So I'm going to go ahead and grab the Maxwell relationship for Helmholtz. Turns out in the Helmholtz expression, we can replace the change in entropy with a change in pressure. And again, that will switch the variables in the bottom. Now, if you remember all the way back to chapter 2 when we were talking about triple product rules, we already showed that the change in pressure with respect to temperature under isochoric conditions is just going to be the ratio of the expansion coefficient over the isothermal compressibility. So, hey, congratulations. I know each of my three terms on the right. It's just going to be temperature times the ratio of my coefficients minus the pressure. Temperature and pressure are measurable. These coefficients can be obtained from tables. Now on the right, well, congratulations. That's just my that's my isothermal Joule-Thomson coefficient. So hey, remember when we said this is a tricky one to obtain? Turns out you can obtain your isothermal Joule-Thomson coefficient as long as you know the temperature and pressure of your system and our expansion coefficient and our isothermal compressibility, both of which can be obtained from table values. So we can go ahead and take something that's very hard to obtain And through some clever manipulations of our fundamental equations and our Maxwell relationships, we can derive a very small and condensed equation. And this is very much the common case with Maxwell relationships. If you find yourself kind of hitting a dead end, especially when looking at variations with entropy, look at your Maxwell relationships, see what your variables are, see if you can pull one out. If you can, fantastic. If not, well, there's some other options, but also don't be aware you may have to pull some older relationships as well. So next time, we're going to go ahead and pick up specifically taking a close look at our fundamental equation for Gibbs. And we're going to go ahead and figure out exactly how Gibbs changes with other variables. Specifically, the next two chapters are looking at how it changes with pressure and temperature. Until then, take care.